With us, we welcome Dr. Hubert Fratzl from First Alpine, High Performance Metals. Hello,
Good
Mr.
afternoon.
Fratzl.
Hello, good afternoon.
And Mr. Marcel Wasserer, the CTO of Enlight AI. Hello.
Good afternoon.
And yeah, we would like to give over the stage to you for your presentation on reinforcement learning in stock replenishment.
Good afternoon, ladies and gentlemen. I'm happy to talk to you about a topic what actually I'm after since more than 30 years, going back to the 80s where the personal computers were just entering the offices and SAP was about to implement R2. And today I'm head of global operations in the Value-Added Services business unit. This is a business unit of high performance metals at First Alpine. Looking back to some experience in various industries and also 5 years in consulting at a company called Accenture.
My name is Marcel Wasserer, so I'm the co-founder and CTO of Enlight. My background is more on the hands-on implementation side. So during the last years, I had the opportunity together with my team to realize around 50 different projects for a broad range of industries. Allow me a few words about Enlight AI. So Enlight is a full service provider around artificial intelligence, and we are based in Vienna and covering the whole spectrum from AI strategy and transformation down to the implementation side. But we do not only apply what's already available in terms of technology. We also picked two specific technologies. This is reinforcement learning and generative adversarial networks, where we conduct our own industrial research and from there transform this research knowledge to actionable enterprise products.
Yeah, a few words to First Alpine. First Alpine is a global steelmaking and technology company in consisting of 4 divisions. The metal forming division is producing profiles and special systems for storage systems. We have the metal engineering division, world market leader in rails and turnouts. The steel division, quality market leader in heavy plates and strip steel. And I'm based in high performance metals, world market leader in tool steel, high speed steel and special materials. Our division, Marcel, yeah, thank you. Our division is very global. It's a very global company with 140 locations around the globe. We had 13,400 people working last business year. This business year is a little bit less, and around about 3 billion turnover. What you see on the picture is the typical shape of our material. So we have round bars and flat material. It doesn't look as high-tech as it actually is. We're talking about a real high-tech product, extremely clean, extreme tough, extreme hard, made for the toughest applications in aircraft engines, oil drills, or high-demanding tool steel applications. This is our geographic footprint. You see the 140 locations around the globe. In every location is signed by a blue dot. And in these locations we have service operations like heat treatment, some also offering coating, texturing. But in every location we have a stock and we have cutting. And in every location, therefore, we have an inventory planner who is ordering at central stocks, and the red dots are our mills where we carry central stocks and produce the steel. Next slide, please. Yeah, this brings me to the base problem or the base challenge we have. We are carrying in our division around about 1 billion of inventory. Our 140 locations are running all SAP, and in all locations we have qualified people doing the inventory planning according to the best knowledge of demand, supply, and efficiency. We have the clear strategy of customer intimacy, meaning we want to deliver fast and reliable customer service. And here comes already the clear issue of our big supply chain. We do have a production time of 4 to 6 months, but we have a delivery time to our customers of 24 to 48 hours. Our typical production lot in a steel mill is around 35 to 100 tons. Our average order size to the end customer is around about 50 kilos. Yeah, we have the last years invested quite a lot in software and people, but still our biggest problem is the bullwhip effect, was what has always hurt us according to the business cycle. Next slide. Explaining the bullwhip effect, of course, you guys are all aware of the bullwhip effect, but it's so important for us that I would like to spend a few minutes with it. And typically I'm using a train model as for showing the supply chain, with the locomotive is the market and we have the wagons along the supply chain, but the wagons are connected with springs, not with fixed connections, is connected with springs. This means when the market goes off, let's assume the market is the automotive market, and people like to buy more cars because they are not so keen to travel in public transport anymore with 100 other people, where in the average 2 of those are carrying COVID-19 virus. So they want to buy new cars, and so the car manufacturing are approaching the tool users to produce a tool for the new car model. But the tool user has to approach the tool maker for the new tool. So the tool maker doesn't have the tool on stock. They doesn't have the steel on stock to produce the tool. The tool maker has to approach our sales stock in order to deliver the pre-material. Typically, the market goes off at all countries, in all automotive companies around the world. So all the tool makers come at the same time to our stock, and we can deliver, when the market really goes off, only a part of it. So the sales go to the central stock asking for replenishment their stock, but they are also asking for even more, because the replenishment models say market goes off, market demand is higher, we have to carry higher stock. And the same happens in the central stock. And in the production, they have to build up a new shift. They have to get the raw material, so they need a few months to build up their production. And then it takes, as I said before, 4 to 6 months to produce. And when they have produced and delivered to central stock and delivered to sales stock and to the tool maker and the tool user who are producing the parts, the market is already shrinking, because the people all have their cars bought and COVID crisis is gone, and basically the production is running, and at the end the production is crashing against the central stock. And that's something what happens. It happens not only with serious crisis, if we have it right now with the pandemic or with the global financial crisis we had 12 years ago. It happens also with business cycles in between. We all know that, and the only thing we can do against it is we have to replace these springs, again, fixed connections. So we have to plan the production according to the market and not according to any supply chain partner in between. Next slide, please. So the next challenge we are actually facing is we have our typical reorder point system for the replenishment. You see the 2 formulas. I think everybody knows that very well. But we have problems with this formula, because with every single parameter you have in this formula, there's something difficult with it. Starting with the demand, as I said before, the demand is not really known. It's even wrong because you have always to look at the end customer demand, and typically you just look at the demand at your direct customer, the next supply chain partner. But this partner is depending on his customer, and this customer is again depending on his customer, and this demand actually is not the real demand, it's just the demand that was created by your customer. Order costs. Who really knows the order costs? Typically you have no clue, or you have an estimate what your order could cost, but the real cost of an order you typically don't have. Inventory carrying costs is depending on interest rates. So what interest rates are you underlying here? You can take the interest rate, what you typically have from the market, from the banks. You can underlie the dividend expectations your shareholder have on the company, what is typically much more than the interest rate, or you can take a WACC, what is typically even more, and you have a big difference, a big variety, and whatever you take, the result of your reorder quantity will be much different. This next, safety stock. Safety stock. What would you take as a safety stock? Do you think your customer would care if your safety stock is 99, 98, or 97%? You can't really say if the customer is more, does he like you more if you have a 99 safety stock compared to a 98%. You just take any number, what you feel is all right, but this is definitely not a mathematical optimum because it's just something out of your feeling. And then it comes to the average. An average is always something what is very difficult. You can calculate everything and can get every result. You just have to take the wrong average and then you get anything. Why? First of all, if you take the average of a wrong number, and we said already the demand is wrong because it's the demand just of your next supply chain partner, then the average is even more wrong than the original number. And to take an average, you have to have a distribution function behind, and typically, because it's easy to calculate, you take the standard distribution, and what you see here on the left end of the standard distribution, it's going to be negative. What does it mean? A negative sales. Actually, we had a negative sales in January 2009. I remember very well. We had more cancellations than orders. What's a disaster? So you can't really survive with negative sales. So in fact, this is something what must not happen. If you have a product where you have negative sales, you have to phase out this product immediately. So this is something what is simple, not relevant for your replenishment. So you have to do something different. You have to have a distribution function like a gamma distribution, what is much more difficult to calculate. You have two parameters to calculate, which again is something what typically is just estimated with the tick sum and not really proven mathematics. Next slide, please. Yeah, and then I come to a very practical third challenge, which are dependencies between our articles. If a typical starting material is what you see here, it's a block of one steel grade. You have one SKU, you get a customer order with length, width, and thickness. You cut it out of this block, so you can cut out of this block any customer order which is within this boundary condition of this block. You can also start with a bar material. If you have the thickness and the width on stock, you can just cut the length. You can serve the customer quickly without major cutting costs. The disadvantage, obviously, you have several hundred or at least 100 plus SKUs on stock. A compromise is plate. With a plate, you have one thickness fixed, so you just cut the width and the length. What you have also to consider, whatever you take, you have scrap, because you have some residual pieces what you can't use anymore, and typically if you cut a block, you're ending up with 15% of scrap. This, in other words, when you buy such a block, you can immediately downgrade the value of the block by 15%, because this 15% is in the average material for the bin. With a bar material, typically you are ending up with only 5% of scrap. So this is much more effective in terms of yield. So you have to answer to yourself 3 questions. The first question is, what is your starting material? Should it be a block? Should it be a bar? Should it be a plate? And typically, it's not even the question one of those 3. The answer might be all 3, because you have high runners. You might like to have a bar. You like to have a block as well to serve the slow moving material, and you might have a plate as well. Good, next slide. Yeah. What pieces are considered as prime stock? You see in the middle the pieces. What is prime stock of this? Might be prime stock, other part might be not. And you have to understand what piece do you take in order to serve the customer properly. Next slide, please. Yeah, so this means that the problem itself is extremely complex and traditionally basically not to be resolved. You have multiple objectives. This means you need to plan in scenarios. Sometimes processing costs are more important than service level. And the next time the inventory is more important. So you have to plan in scenarios, and you have the uncertainty of in demand and supply, and as well the uncertainty in your stock. What should be an acceptable safety stock, and in your operation, if something happens, this uncertainty you always have. So our new approach is now we are looking into reinforcement learning, and we hope that we will as good as the best planner, or maybe even better than the best planner, and we will also cope with the high complexity in the inventory. Marcel?
Yep, thank you. Then I will take it from here. So in the next around 10 minutes, I will try to introduce you the basic concepts of reinforcement learning and how we applied this to the stock replenishment problem. And yeah, this will be a more technical part. And after that, Mr. Fatzl is going to take over again and present the first results we are seeing from this approach. But first, let's ask the question, why do we need reinforcement learning at all? So one of the main motivations to use reinforcement learning here is because reinforcement learning can be scaled to very complex problems. And this can be explained partially because it uses the same underlying neural network structures that are already established in other domains like image recognition or text. And we can, also in reinforcement learning, we benefit from the same advances that we saw there during the last years. And neural networks are feature representation learners, which means that we do not need to explicitly program domain-specific knowledge into the systems. Instead, otherwise very complex to realize things like the consideration of global interdependencies can be recognized in a very natural way. The second big advantage is adaptability. So we can use very flexible cost terms and combine them freely. And also the reinforcement learning framework promotes the emergence of long-term strategies. This is because we are not only looking into the performance of an agent in an instant of time, but instead we assessing the performance of the agent over a longer period of time. In our case, it's more than a year, and only after we looked at the cumulative performance of the agent in every single day, we decide, also the algorithm decides in which direction it should progress. And the last point on this list is, of course, just a requirement from any real-world process. So we need to deal with uncertainty. Any real process is unpredictable after some point. And fortunately, most reinforcement learning algorithms are able to handle the uncertainty. And also during the training process, I mean, the agents implicitly need to pick up a good strategy to cope with uncertainty, because otherwise they would just not perform as other agents do. Then let me briefly walk you through the reinforcement learning framework and show you some historical milestones, so to say. So the history goes back to the 50s, like with almost all machine learning methods. But for us, it's getting more interesting around 2013, when the first simple video games have been solved with reinforcement learning. So this is on the upper left corner, you see an example of an Atari game. Of course, still a simple game and still little to no relevance to the real world. But the methods has been scaled and evolved since then. It has been applied to Go, to StarCraft, and also to Dota. And those three games might you might not be that familiar to those three games, but all three games have very well financed professional leagues behind them, and those systems have been able to beat the world champions there. And this can be seen as a proof of concept that it's possible to come up with really, let's say, complex new strategies, because otherwise this would not have been possible for those systems to beat the best human players under equal circumstances. What does this have to do with our logistics problems? So games and real-world processes are both sequential decision problems. Of course, in order to tackle such a problem, there are a few more prerequisites to be met. But in general, reinforcement learning is able to, also with reinforcement learning, it's possible to address the majority of real-world problems, as long as there's a simulation available, but more on that later. So let me quickly introduce the single most important concept of reinforcement learning. This is the agent-environment interaction loop. And I will walk you briefly through with three simple questions. So first, we need to decide where we want to optimize the system. And this is usually simple answered because we have an established process that we want to optimize. And the representation for that is the environment. The next question is, what do we want to optimize for? So of course, it doesn't make sense to optimize the environment as a whole. We need to say and to tell in cost functions and other metrics to guide the optimization process. And this is done by the reward that can be seen as a scoring system. Also, the state is important in our case. The state should contain all information that's necessary to come up with the actual decision. And this is the last part, the how to optimize. This is the responsibility of the agent. From the top level concept, it's quite simple. We just expect the agent to come up with the best possible sequence of actions. And the reinforcement learning algorithms, of course, need to take care that this goes into the right direction by really learning interactively from interaction. I would like to take a minute and contrast this with supervised machine learning, which is at the core of most established machine learning solutions. Assume we have a simple classification system, image classification system, and we present an image of a cat. Of course, we expect the classifier to predict the label cat, and this is a simple process. We can also immediately decide if the label is right or wrong. Below, we see the situation for a reinforcement learning agent. Let's just assume we present initial state of a tic-tac-toe game, and the agent should tell the next move and decides to take the center move. Now at this point, it's hard to provide direct feedback to the agent, because we just need to walk through the development of the game, and only afterwards we will be able to judge the performance of the agent. And from there, it's intuitively clear that reinforcement learning is an entirely different class of machine learning. And I think most of the fascinating use cases that have been shown at this conference, in general, powered by prediction models. And we are just at the beginning to see the adoption of this reinforcement learning framework that can also go one step further and optimize whole strategies into the industry. But now let's look more specifically to the stock replenishment problem and how we address this. And for that, the most important component is the simulation. It's also, let's say, promoted under its more fashionable name, digital twin. And this picture should already look familiar. So this time in the blue box, we have a specific version of the environment, the replenishment environment that contains all the mechanics that's necessary to simulate the replenishment process. And up there is now the replenishment agent with concrete actions. So this agent is queried every single day to come up with a list of products and quantities that should be ordered and should be purchased. But this system does not live in isolation. So we are interfacing with the customer order cycle, with the production cycle, and those are systems that are already established. So the aim of such projects is not to redefine the whole, let's say, the whole process. So this is not what reinforcement learning can do. Reinforcement learning can take an existing process and make the optimize for the best possible decisions to be made within those existing landscape. And in our case, we are embedding our system into an existing SAP system. Just a few more words to the simulation environment, because it's of such importance for this kind of projects. So we are training our agents for millions of simulated years, which means that, of course, that the digital twin needs to be fast, but not only fast, it also needs to be very close to the reality, because otherwise we cannot expect that we take an agent out of this training process, deploy it in a real system, and get a reasonable performance. So this is really the most important component. And today, unfortunately, suitable digital twins are really a rarity. So it feels, at least from the development side, it feels a little bit like the pre-ImageNet era, where there have not been big data sets out there. And I think this, we will see the emergence of much more practically usable digital twins in the upcoming years, just because this is it's just the next logical step after aggregating the data. And what are the costs that are going into the reinforcement learning system that we are targeting our optimization? So, of course, we need to look at the inventory cost. That's quite clear, because we want to reduce the stock levels. We also need to avoid the trivial solution. So that would be zero inventory. So we also need the stock out costs to cover for that. So because zero inventory would lead to 100% stock out, we need to balance somehow those two terms. And also we need to balance the inventory cost with the cutting cost. As we saw earlier, Mr. Fassel showed us the two different strategies with actually three different strategies with plate, blocks, and bars. And there is a large trade-off, and it's not only related to the article, also to the let's say product that are produced, but also to the intermediate products that are the result of this cutting process. So the agent faces multiple conflicting objectives, and our way to treat this is to introduce weighting factors. And on top of that, we are also calculating KPIs similar to the KPIs that are used in production to be able to compare our performance to the real system. And just as a side note, some costs of the real process, so there can also be the situation where it's easier to measure the cost in the simulation than in a real environment. We see this, for example, in the real demand versus the consumption. So we do not know the real demand of the customer. We only know what has been sold. And also sometimes it might occur that customer orders do not materialize. So, but this, of course, it's not feasible to track all kinds of reasons that could lead to that. So I'm coming towards the end of this technical part, and the last remark is on the agent. So far, we only discussed the replenishment agent, but during the project, we found out that also the cutting, also the make-to-order process, has a very large effect on the performance of the inventory management. And yeah, this. Fortunately, in the reinforcement learning framework, it's also possible to train multiple agents at once and to align these agents with a common objective structure. And this is exactly what we did here. So we trained those two agents from scratch for millions of years. And yeah, so starting from pure random try and error, it was also for us from a technical point of view, it was quite surprising that we got very, let's say, good performing agents working towards a common goal at the end. And from that, I return to Mr. Fratzel.
Yeah, the proof of concept has shown that we will reduce inventory at minimum by 10%. We also will reduce some cutting and material handling. And what's also quite important for us is we will have a proper knowledge exchange between, or a knowledge conservation of our best planner, and the best and experienced planner are typically those who are close to retirement. So we will have all that in our AI tool, and now we are in the process of implementation, and we will see if it really materializes.
And I would like to finish this presentation by giving an outlook into other fields where reinforcement learning could achieve a high potential. So now we had an example of inventory management. This is especially interesting in cases where the materials are dynamic, as we have seen in this case. And this is not only relevant for the steel industry, because of course this is also relevant for the wood industry or for the chemical industry. And another class of problems we are tackling are vehicle routing problems, especially if they have a very dynamic and short planning horizon. And we are working on production cases, like job shop scheduling is a kind of very general formulation of all kinds of production problems. And again, it's interesting to use reinforcement learning in those cases once we have a structure that produces complex dependencies that has a dynamic nature in the planning process. And one last remark, also what we experienced in the last years globally, there is currently no software stack available to work on these kinds of applied reinforcement learning problems. And as we want to see more adoption in the industry, we decided to open up large parts of our technology as an open source project. We call this the open source framework Maze. And this is available as an early version on GitHub. So this might be especially interesting for the data scientists and machine learning practitioners listening. This brings me to the end of the presentation. Thank you.
Thank you so much. Quite a lot of information, Hubert Fratzel and Marcel Wasserer. And people starting to send in questions. Not to forget that we have 1 minute delay with our video stream. Let's have a look at the questions. And here they are. Okay. The first two questions actually touch upon the topic of SAP. For once, how to integrate the solution with SAP, and for once, Nicola asks about the methodology. Can you shortly elaborate on that?
Yeah, we integrate with the SAP MRP process, and in some sense, we override the basic planning that is done there. But we do not really change the planning parameters that are collected there. So because SAP is a much more complex, involves many more, let's say, input and output parameters that are relevant for us. So we focus really on the purchase requisition decision in our case. And for the second agent, this is some module that has been developed internally that is interfacing with an internal component that's used in the make to order process.
All right, thank you, Marcel. And we move on to question number 3. Long Fei asks, compared with traditional approximate solutions such as MIP, mixed integer problem, solution in operations research, how much progress has reinforcement learning made?
That's an interesting question, because actually I just, as I read about 1 year ago, that also one of the largest commercial mixed integer programming solver are now using reinforcement learning internally to optimize the cutting planes. So it's somehow found its way to the mixed integer programming community or to these tools, but there are other aspects that are treated with reinforcement learning that mixed integer programming usually cannot cover, like this uncertainty. It's not that easy, also it's not easily possible with mixed integer programming to formulate different, let's say, potential futures, and this is something that reinforcement learning can do.
All right, and for the next question, Ruth asks, how long do you think the applied reinforcement learning project will take to reach a reasonable outcome from start to finish? I guess this question is for Hubert Fratzel.
Yeah, that's a difficult question. We took now around about 8 months to get the real result out of it, but we are already working on this for 6 to 8 months. So probably you can do it faster, but I think to really get enough deep into the problem and to get a broad understanding how to solve it, I think you should calculate at least a year or a year and a half.
I can add to this one more point. I think also that from the effort side, from the pure development side, what is causing the most effort is really the digital twin modeling, and this is something that, yeah, the companies could also start work on their own, especially because reinforcement learning is for sure not the only field that would benefit from digital twin.
Interesting take. And an additional question to Marcel. Applied reinforcement learning doesn't sound like the typical startup topic. How did your company decide to pursue that route?
Yeah, that's an interesting question. No, for sure, it's not the typical startup topic, and there's really significant effort going into this direction.
What's the typical startup topic? Can we ask Mr. Anonymous what?
No, it somehow originated from this idea of the AI lab. So we already did at this time industrial research, and we are also well connected to the research community in Europe, to Hochreiter, and also to the ELIS network. And from that, somehow it became, it got its own dynamics. And now with the framework, we are at a point where we can really, let's say, give something back to this community.
All right. Well, that concludes the Q&A session for now, unless we don't receive any further questions. Any final remarks from your side, Marcel Wasserer and Hubert Fratzel?
Yeah, from my side, I want to mention that we are very pleased with the cooperation with Enlight. I think we are really making progress, and it's not easy to understand our business. It is quite complex. Also, the material looks simple. So yeah, and now the next months will show if we really can materialize what we think.
All right, thank you very much. And funny thing, I saw Marcel's camera overheated, but can you still hear us?
Yes, I can hear you.
Now you look healthy again.
Yeah, I would also like to thank Mr. Fratzl and this to give us the opportunity to work on this topic, because I think at the beginning when we started to work together, it was not much more than idea to look into this topic, and I think this is making also it's one of the first use cases I think globally that really tries to apply reinforcement learning at that scale.
Thank you so much, Marcel Wasserer and Hubert Fratzl. We wish you a good afternoon. Please stick around for the B2B meetings, and we head right on to our next and final session with a short intermittent video.
Yeah.
Talk to you in a second.
See you in 2 minutes.
Bye-bye.
Bye.
Bye.